In this video, I would like to talk about angle between planes, and we will solve this specific question: what is the angle between planes ABC and DBC? So there are ways to solve this question, but I would like to go into the pure geometrical way, and then I would also discuss the vector approach, the normal vector approach. But I would like to explain how both of these are the same thing, and what are the complications, what are the small uh, like small pitfalls you can fall into in while solving these kind of questions. So let's explore it. First of all, we will explore angle between lines, then angle between vectors, and then we can easily understand angle between planes. So let's first think about angle between two lines. So suppose that you have these two lines which are intersecting, and you can see that there are these four angles between these two lines, and it's pretty clear that if you know any one of them, you can figure out all these four angles, because if this is x, this is going to be x, and this is going to be 180 degrees minus x, because this is a linear pair of angles. So these two angles should add up to 180 degree, elementary geometry, and this is also going to be 180 degrees minus x. So you can say that between two lines, two intersecting lines, we have in general two angles, an acute angle and an obtuse angle. Like here in this figure, we have the acute angle 40 degrees and obtuse angle 140 degrees. Let's rotate one of our lines and see what happens. Then you see the acute angle has increased and the obtuse angle has decreased. This is to 70, this is obtuse angle decreased to 110 degrees. Then let's rotate even more. You see, I am not rotating this yellow line about this point of intersection. This point of intersection is also moving. I am rotating about some other point. This is for a purpose, you will see. So now, before this was 70 degrees, acute angle was 70 degrees and obtuse was 110. Now I have rotated it, and this I think this is the special case when the lines are perpendicular, and the point of intersection you see is here. It's moving a little bit. Okay, so both the angles, acute and obtuse angle, in this beautiful situation is 90 degrees. It's a very useful situation, like perpendicular lines. Perpendicular lines, we use it a lot, and in pure geometry we talk about like how to draw a line perpendicular to other line, and it's not that easy. It's pretty simple, but this is a very useful geometry, two perpendicular lines. Okay, now let's move on to, I rotated this line even more, and then the acute angle, like where you were getting the obtuse angle, you were getting the obtuse angle on the left side. Now you see you will get the acute angle on the left side, and so that angle is continuously decreasing, and now the acute angle has become, let's say, 30 degree and obtuse is 150. Then decrease it even more. Okay, what happens? 10 degrees, 170 degrees. Okay, what is happening to this point of intersection? It is moving now at a very faster rate. Now 5 degrees and 175 degrees, it's moving, it's moving at a faster rate, okay, with decreasing acute angle. And then you can say that when these two lines get parallel, I mean, if this angle theta, this decreases down to 0 degree, this point of intersection will approach to infinity, and in that case you can say that these two lines have become parallel. Okay, and in that case you can say that the acute angle is 0 degrees and obtuse angle is 180 degrees if required. If not, you can simply just say that there is no angle between these two lines. Okay, now let's move on to the angle between two vectors. So if you see two vectors, important fact is that two vectors can never be coplanar. I mean, they can be anywhere in some different planes, but they can always be made coplanar. Okay, so it's like, maybe suppose you have two vectors. Suppose you have a cube, and you have a vector somewhere here and another vector pointing in some other direction. They don't look coplanar, but if you move this b, translate this b in such a way, you can bring these two vectors, I mean, in such a way, let's bring the tail of b to the tail of a, then definitely you will see that these vectors have become coplanar because their tail is matching, and the two heads, the head of a and the head of b, if you join this common tail and these heads, you will get a triangle, and you will see that they have become completely coplanar. Okay, so this is not an oversimplification. I have taken two vectors in the same plane. So now you can see like if you draw lines along these vectors, then they intersect at this point. Some point they will intersect if they are not parallel, and in that case you will have four angles again. But you can't use this time one acute and one obtuse angle, because you see from this point, this direction, this vector, yellow vector is going in this direction, the blue vector is going in this direction, so it's better to use just this angle, the obtuse angle. So you can skip the acute angle, and sometimes you will have to skip the acute angle the obtuse angle, and take the acute angle on the basis of direction. So you give importance to their direction, and then you choose one of these angles. So you don't think like there are two angles between these vectors. More simply, you can if you don't want to draw these lines, you can just join their tails, or maybe just join their heads, and then you will see that the angle between the vectors, which is both the same. You can join the tails also, you can join the heads also, okay, and then find out the angle between the vectors. So somebody can also say, maybe like, if this is 30 degree, this is 330 degree, why not take this angle? I mean, it's better if you keep the angle in the range of 0 to 180 degrees. If you don't use these bigger angles, then you can always have the angle between two vectors in this range, 0 to 180 degrees. So this will be a nicer approach, simpler way, okay. And so basically, theta acute, theta obtuse, no, you don't have to do this for vectors, because it's either an acute angle or an obtuse angle, or maybe if in the special case the vectors are perpendicular. So here, let's say your theta is 140 degrees, okay. So I will show you, like, if I start rotating the blue vector, then you will what angles would you get between two vectors? If we rotate it a little bit like this, you get 160 degrees. Then you rotate it like this, you get 180 degrees. This is a very special case. You can say that the vectors are anti-parallel. They are moving in exactly opposite directions, okay. And then you can rotate even more, and then the theta is 110 degrees. You take this angle, not that angle. This angle will be 360 minus 110 degrees. Don't use this bigger angle. So 110 degrees, then decrease it down to 30 degree, and then 10 degrees, and then eventually 0 degrees when the vectors get parallel, okay. So angle between vectors is unique. You can't use two angles between two vectors. Just use one smaller angle, and that angle would lie in the range 0 to 180 degrees. So 0 for parallel vectors and 180 for anti-parallel vectors, okay. Now let's move on to angle between two planes. This is the real deal. This is what I want to talk about. So if we have two intersecting planes, first of all, notice that there is a line of intersection. And the most general kind of idea I see when students are dealing with angle between two planes is like they think about the edges of the plane. Like, this is the edge of the yellow plane, this is the edge of the blue plane, and then they figure out this angle from here. But is it okay? Then there is another idea, like suppose like on the line of intersection you have some point, and from here you can take any line on any pair of line, one on the first plane and one on the other, and then you can figure out the angle. They will be the same, and they will be the angle between the planes. So I would like to talk about this. Is it so? First of all, let's think about, like, if you have these two planes and then you are taking the edges of the plane, and this angle theta, you say that this is the angle between the planes. But I want to emphasize that the planes are infinite. Why this thing happens is like when you are dealing with these geometrical figures like cube or a tetrahedron. Suppose you are dealing with a cube. So you see, this is a plane. This is not a plane. This is the face of the cube, and the plane is infinitely extended in all other directions. So the face of the cube lies in some plane, some infinite plane. And when we are thinking about angle between the planes, we can I mean, the face is enough also. We can figure out the angle using the face, but the edges of the face does not matter because the plane is infinite. So you have any plane like this here, you can extend it infinitely, and you see that this line is no longer on the edge of the plane because there is no edge of the plane. And similarly, this yellow plane you can extend, and this line is no longer on the edge of the plane. So these two lines which we are thinking as edges of the plane can become any two lines on the plane. And will it be valid? It would be to take this angle as the angle between the planes. I mean, if you draw any two lines on these planes through a point on the line of intersection and the angle turns out to be equal, then that is okay. But is it so? Let's think about that. So we have a cube and these two planes, and it's very intuitive to feel that these two planes are perpendicular. I think everybody can feel that. So let's figure out, let's take this line of intersection, like let's focus on this point, and from here I can draw some lines. First I will draw these two edges, and this is very simple, and these two edges are inclined at 90 degrees, so they are giving us the right angle, the right angle. So the angle between these two planes intuitively you can also feel is 90 degrees, and these two edges are actually giving you the right angle. But then we will have to check for other kind of lines also. For example, this face diagonal and this edge. How about this? Is the angle, how much is this angle? Is it still 90 degrees? Well, so you can say that this yellow plane, look at this yellow plane, and look at this edge. You can feel very simply that this line, let's say this is AB. AB is along the normal of the plane. AB is normal to yellow plane. So a normal, suppose you have a plane and then there is a normal to the plane, so it will be perpendicular to any line on the plane, right? So that is the basic idea, and because of that this angle is still 90 degrees. So this angle is still 90 degrees. Maybe if you want to do it in some other way, something like this. So this edge length is A, this the length of this face diagonal is root 2a, and when you join these two ends you get the length, the body diagonal, which is of the length root 3a. And you can see that root 3a squared is equal to root 2a squared plus a squared. So you see that if I mark this, right, ABC is right angle triangle because it's following the Pythagoras theorem, right? And this should be right angle at B because this is acting as hypotenuse. So again you get the angle 90 degree basically. So you might feel like if you do this kind of exploration, you might feel like I can take any two lines on the plane. For example, if you go and take rather than this line on the yellow plane, if you take this line also, which is the line of intersection which lies on both the plane, then again your angle will be 90 degrees here. But you see, this is where you can argue, why can't we take like both the lines on both the planes to be the line of intersection, and then we will get 0 degrees angle? But then you would be like, maybe just exclude, don't use the line of intersection. Okay, let's not do it. Then now I will think of this case like, how about this line and this line? This red line is on the blue plane, this red line is on the yellow plane. And what is the angle between these two lines? Well, how can we figure out? Just join these ends. And you see that this length is root 2a because this is a face diagonal, this length is root 2a because this is a face diagonal, and this length is also root 2a because this is also a face diagonal of the back face. And because of that, this angle is 60 degrees because you have an equilateral triangle here. If ABC is equilateral, all the sides are of same length. So you see now this time you don't get 90 degrees, which means that the idea that you can take any two lines through a point on the line of intersection of the two planes, and using those lines if you figure out the angle between the planes, that will not be always correct. So focus on this idea, think about it a little bit, feel it. We can't just take any two lines on the planes and say that the angle between them is the angle between the planes. Okay, now let's move on to So what kind of line should we use? What kind of line should we use? We will always be using, I will always be using this line of intersection of planes, and from a point on line of intersection I will draw some two lines in a very special way, so that I can get the correct angle between the planes. But what do I mean by correct angle between the planes? Intuitively, let's say if we are rotating one of the planes along a line which is the line of intersection of two planes, and if I start rotating this let's say the yellow plane, and you see what happens, the angle, you can feel that the angle here is a little bit, and then the angle is increasing. We still don't know how to exactly write this angle, but you can feel it intuitively that the angle is increasing on one of the sides, and then eventually the angle goes to 180 degrees. Here I would like to say that the angle has become 180 degrees on this side, and here I would say, like in this limiting case, I would say that the angle is 0 degrees. So if we want to measure the angle between two planes like this, which is very intuitive, just like before how we did with lines. So if we can have two lines from a point on the line of intersection of two planes in such a way that they give us this 0 degree and 180 degree here, then that would be good enough, right? Then we can understand how the angle between the planes is increasing and decreasing. That would be good enough for me. So okay, let's think about this. What if I take a line something like this? So when the yellow plane is coincided with the blue plane, this line and this line, they are exactly on top of each other, so making an angle 0 degree. Great. So here you can see that this will tend to 0 degrees, and then if you go on increasing the angle between the planes, this angle is also increasing, this angle is also increasing yet, but it doesn't fall down to 180 degrees. This is not 180 degrees. I mean, somebody can say you can measure it from going up, and then you can say that this is 180 degrees, but this is a plane angle. We are going to use a plane angle, and a plane angle between two rays is defined in its plane. So I will have to measure it like this, and this is not 180 degrees. Okay, so using plane angles only, I can show you how we can have such a line which will give us the correct angle between the planes. Okay, now let's think about this. We have two planes coinciding, and then we have taken two lines in such a way that when they are at 180 degrees, okay, and now we want to rotate the plane in the opposite direction and see what happens. If we take any such line, this will not be enough, because you see I have taken a general line like that, which on coincidence of the planes give the angle 180 degrees, but when you turn it back, the angle does not fall down to 0 degrees. This is not 0 degrees. So okay, so these lines we should not take to measure the angle between the planes. What should we do then? So the simplest idea is like use perpendicular lines, right? So this is your line of intersection. This is your line of intersection of planes, and take any point on the line of intersection of planes and use two perpendicular lines, two lines, one in each plane, which is perpendicular to the line of intersection of the plane, and then you will see that this 0 degrees and 180 degrees criterion will hold. These two lines being always perpendicular, and then you see they start from 0 degree and they fall down to 180 degrees. So this is how we can define geometrically the dihedral angle, or the angle between two planes. You go to the line of intersection, you take a point, you take two lines, one in each plane, perpendicular to the line of intersection of planes, and then from there you can measure the angle. This is the angle we are looking for. You can also extend these straight lines, and you can also see that you have two angles between the planes. One is acute and the other one is obtuse. Okay, so just by using angle between two lines, we can define angle between two planes. Okay, now let's move on to some practical examples. Suppose this is an open book and these pages are some planes, some part of some bigger plane, and what is the angle between these two planes? So if you use these two lines to measure the angle between these two planes, I think this would be okay here, because these lines, this is the line of intersection, this part here, and then this angle is 90 degree because the pages are rectangular, and this angle is also 90 degree because the pages are rectangular, and this is the correct way of measuring the angle between the planes. Okay, but if you are on a roof and you have so many planes here on the roof, you see this plane, let's say P1, and some plane here, this is P2, this plane here is P3, let's say there is a plane on the back side also P4, and we want to figure out the angle between P1 and P4. Can we use these lines? So just go here and check whether this angle is 90 degree or not, because this is the line of intersection of the plane, and these black lines should make 90 degrees angle with the line of intersection of the planes, and then only we can measure the correct angle. And it feels like this is 90 degree in this diagram, so this is the correct way. But if you are measuring the angle between these two planes, this plane and this plane, and you're using these lines, this is not correct, because you see this is your line of intersection and the angle is not 90 degrees there. You can pause the video and think about it. This is not right. Also, how about these two lines to measure out the angle between these two planes? This is the line of intersection. They don't look perpendicular. You can feel it by how this roof has been made. They are not perpendicular, and then this is not the right way of figuring the angle between these two planes. Best would be, you know what, take a knife, take a big knife and go and this is your line of intersection. Put your knife in such a way that this is perpendicular to the line of intersection and hit it, and then you will get two lines there, and you can figure out the angle between those two lines. Yeah. Okay. Now, angle between two planes using vectors. We have seen using pure geometry how we are doing it, and now using vectors. So you see on the plane there are many directions, but it's better to use the normal direction, because then there will be only two such directions. So you can say that you can use the normal direction of a plane to figure out angles between the planes. Okay, so which normal you want to use, it's up to you. Let's now think about this. So this is the diagram in which these lines which are measuring the angle between the planes are perpendicular to the line of intersection, and then from here, like let's think about this point, and from here we draw a normal to the yellow plane. Okay, so once we have drawn this normal, this is 90 degrees. Let's take some point on the normal to talk about, and let's think about this ABC point. So these ABC points are coplanar. Any 3 points are of course coplanar. And what is the normal to this plane? So you see that this AB is perpendicular to this line of intersection, red line. Let's call this L1. And you see that BC is also perpendicular to this red line. So you can understand that if you even draw this AC, this whole triangle, this whole plane in which A, B and C are, they have this normal L1, because two of the lines of this triangle are perpendicular to this line, and this line definitely will also be perpendicular to L1. AC will also be perpendicular to L1. Okay, so this L1 is normal to the plane containing A, B and C, right? And then let's think about some other points, B, C and D. B, C and D are also coplanar, because any 3 points are coplanar, and you join a triangle, make a triangle like this, and you see that BC is perpendicular to L1, and CD is also perpendicular to L1, because L1 is a line in yellow plane. Okay, and DC is normal to the plane. DC is normal to yellow plane. and because of that you can say that BCD are of course coplanar, and the normal to this plane is also L1, right? You can think about this like if you have a triangle and from go to any one of its vertices, like, or not even yeah, go anywhere, like think about this plane. So the normal, if you think of a line which is perpendicular to this line and this line also, then this will always be this normal of the plane. There's no other line which is perpendicular to both of these lines, and this normal is also going to be perpendicular to this line also, the third line also, third line of the triangle. So this you if you want to think about it, pause the video and think about it, be very sure about this. You can feel it very intuitively. So we have L1 also normal to the plane containing BC and D. So you see ABC plane and BCD plane have a common normal, which means that ABCD are now coplanar. Okay, so far so good. Then we draw a normal at A, and then using the same kind of logic we can show that so we first of all we are concerned about whether these two normals will intersect or not at the normals emerging from point A and point C. So using the same kind of logic as we did, take another point E here, show that A, B and C, before we showed that we have shown it, A, B and C they are coplanar, and L1 is normal to the plane containing A, B and C. And now you can also show that triangle ABE or the plane containing ABE also has the normal L1, because AB is perpendicular to this line and AE is perpendicular to L1. AE is in the perpendicular direction to L1 because L1 is a line on the blue plane and AE is the normal to the blue plane. So using that logic, we can say that AB, C and E are also coplanar. So AB, C, D, E are coplanar. So there will be a point of intersection here, right? Let's mark that. This is the angle between the two planes which we have already talked about. And so you see if these are planar, so think about this ABC and this is, let's say, F. ABCF quadrilateral, and if this angle is theta, this angle is going to be, these angles are already 90 degrees. So if the sum of all the angles is 360 degrees, so if this is theta, this will turn out to be, this angle will turn out to be 180 degrees minus theta, right? And that you can see is the angle between the other angle between the planes, and here also the angle between the normals is 180 degree minus theta. But if you take if you reverse one of the direction of one of the normals, you will get the other angle theta. So basically what is the angle between the planes here is the angle between the normals of the planes. Okay, so from here now we can go and solve this question. So this is a question, what is the angle between planes ABC and DBC? We have been given these points, and let's draw a perpendicular from point D to some point on the line of intersection of planes. And let's think about that. Let's say that this point is M. Let's first figure out what is this DM length. How can we figure it out? Let's say that this angle is theta. You see triangle DCB is right angled at D, and there you can use some trigonometric ratios, and you know that this length is 2 because this coordinate is 2. You know that this length is 3 because this coordinate is 3. This length is 1 because this coordinate is 1. So first of all you can figure out tan theta, which is just a minute. Yeah, tan theta, which is going to be 3 by 2, and then from there you can figure out sine theta and cos theta also. And then now you can go into the triangle. How do I write this DM? I go into this triangle DMB. This is right angled at 90 degree. As you can see, we have drawn it, constructed it like that. And then this is the hypotenuse, and dm with respect to this angle theta, dm is the perpendicular, so you can see that dm is 2 sine theta. So we have dm. Now we are thinking about, if I draw from this point a perpendicular to the line of intersection of the planes, where will it fall? Will it fall there, or will it fall at M, or will it fall on this side? This is something we need to think about. It feels very like, do you feel that it will fall at M? But we need some reason to believe in that. So let's think about this. What is happening here is like, I mean, the reason is pretty simple. AD is normal to the plane, normal to the red plane. So red plane, and there is a line on this plane. Let's say BC is the line on the red plane, and you are projecting the normal to on this line. And if this is a true normal to this red plane, the projection of that normal would be 0. The length of the projection would be 0, and this is pretty easy to verify. I will show you with an example. Suppose this is a plane and this is a normal, and then you have a line on the plane, and you project in this project the whole normal on this line. In this case, you can simply see that the projection is 0, because the tail is already projected. You don't have to project the head. Head is also projected at this point only. So, but what if the line is somewhere else? So then you take project the tail first, something like this, and this angle turns out, this angle is 90 degree because you're doing projection. And now you can think like, where would the projection of the head fall on? So you can see very simply that this whole situation is symmetric about this line. This is the line of symmetry. So if you say that there is a 90 degree angle on that side, then there will also be a 90 degree angle, or a line which will make a 90 degree angle on this side. But that cannot be the case, because you don't have a, like, there is a point and there is a line, there is only one perpendicular, one shortest distance from this point to this line. So because of that logic, I can say that you cannot have two perpendiculars from a point to a line. So you should better have your perpendicular right here at the line of symmetry. Okay, if you want some algebraic calculation, something like that, you can say like this distance is d and this distance is h, then this distance will turn out to be root under d square plus h square. Then let's say you are taking, you're going somewhere here from this line. Let's say this distance is x, and then you see that this is 90 degree, this angle is 90 degree, this is d, this is x. So this distance will root under x square plus d square. And from here now you can figure out that this is a normal to the plane, so this is going to be 90 degrees, this is h, this is x square plus d square. So this length, which length? Let's say this AB, this length is going to be root under x square plus d square plus h square using Pythagoras theorem. And now you look at this, let's say this point is M. AMB, in triangle AMB, Pythagoras theorem is being followed. You can check that AB square is equal to AM square plus MB square, which will tell us that there is a right angle at M. So angle AMB is 90 degree. Okay, so this way also you can prove that the perpendicular has fallen at this point only. The perpendicular from the head has fallen like that, at that point only. Okay, so this normal may not have its foot at the plane. This could be something somewhere here, but basically two lines going in perpendicular direction. This line is along the normal of the plane, and this line is on the plane. Two lines going in perpendicular direction. If you project any part of one of the line on the other part, on the other line, the projection would be 0, which is basically, in terms of vectors, we say that A dot B is 0 if A is perpendicular to B. Okay, so let's come back here, and then we now know that AM is going to be perpendicular to the line of intersection also. And now we can figure out the angle between the planes because the criterions are correct. We have a point of intersection we have a point on the line of intersection, and we have taken two lines, AM on the blue plane and DM on the red plane, in such a way that they are perpendicular to the line of intersection of the planes. And now you can say that this angle alpha is the angle between the planes. So that you can figure out using simple trigonometry. We have already figured out what our DM is. So tan alpha, you see, tan alpha would be AD by DM. And when you do that, AD is basically 1, DM we have already figured out, 6 by root 13. So you get your tan alpha, from there you can get your sec square alpha, and then from there you can get your cos alpha to be 6 by 7. Why I am writing this result in terms of cos inverse alpha? Because mostly this question students will be doing in terms of vectors. So I will verify that using vectors you will also get the same answer. So let's go into that. What would you do when you are using vectors? So you can use some pretty shortcut tricks, something like the equation of ABC. If you are looking at this plane ABC, it has an x and y and z intercept of 1, 2, sorry, x intercept is 3 and y intercept is 2 and z intercept is 1. So you can write the equation of the plane like this, and then from there you can extract the normal to the plane, and you can think about plane DBC now. Its equation is z is equal to 0 because that is basically xy plane, and the normal is k cap. So you have n1 and n2, and then using the angle between the two normal vectors you can figure out. And to figure out the angle between two vectors, people generally use this cross dot product. You can also use cross product, there's no problem with that. So you see, then you figure it out, so you get the same angle. But there is a lot of background knowledge involved here. Like, why do you write the equation of plane ABC like this? You will have to prove that. You will also have to prove like why the normal of the plane of this equation, which has this equation, why the normal of this plane is like that. You will also have to prove like why do you do this dot product like this, n1 and n2? Why only the k components multiply? Why not the I and j components? Think about that. And then you can also, so basically there is a lot of background knowledge involved here. This is not pure geometry. You are using a lot of results from vector algebra. Okay, so I will show you like how this geometrical approach is very easy to figure out some dihedral angles. For example, in this regular tetrahedron, if I have to figure out the dihedral angle, I can do it very easily using geometry. What I will do, like this is your plane 1, first plane, and the second plane. All the planes will be equally inclined, that you can feel, because the tetrahedron is regular. So what is the angle between plane P1 and P2? So this is the line of intersection. You take its midpoint and you can see that the perpendiculars, this is an equilateral triangle. Triangle OBC is an equilateral triangle. So its median is also the altitude. This median is also altitude. So this is the median, which is also the altitude. So this angle is going to be 90 degree. So then again, the other perpendicular line you can figure out. But first of all, let's think about the lengths. OC is, let's say the edge of the regular tetrahedron has a length A, and then this length will be root 3a by 2. You can simply see that this is going to be 30 degrees, so you can take a cos 30 degrees. So, and then the other line which is perpendicular to the line of intersection of the planes is this AM, let's call this M, and that length is also going to be root 3a by 2, and then you can figure out this angle very easily, this angle theta very easily. Complete this triangle. So these triangles are everywhere. Even in 3D you can take triangular slices and then figure out the angles. So this angle theta you can now figure out using the cosine rule. So in a triangle ABC, if you want to write cos A, you will have to write B square plus C square, these adjacent sides. If you are thinking about this angle, first think about this B and C sides. B square plus C square minus A square by 2BC. Okay, and this is the same thing which I have applied here. This is a very interesting formula. I love to use it a lot. So from there you can figure out that the cos theta is 1 by 3. So theta is basically cos inverse 1 by 3. If you use the vector approach, then you will have to figure out like how to draw a regular tetrahedron. So you can use these vertices of the cubes to draw a regular tetrahedron. There is a video on my channel explaining this, how to draw these platonic solids inside each other. So you can, I will post a link in description, you can take a look at that. And from there now you can figure out the coordinates of the vertices of the regular tetrahedron, and then you can figure out these vectors along these edges of the tetrahedron, and then you can do the cross product to figure out the normal vector. For example, here let's say this plane is ABC and we have these two vectors. We are crossing this and this A and B vector, so then you will get a normal vector to the plane ABC. So that you can do, and then you can figure out some other vector, and then you can figure out the normal vector of the other plane. And then you see a lot of mechanical work you will have to do here, like robotic, and it's you don't have that wow feeling with this kind of method. So then you do the dot product of these two vectors, and then you use this AB cos theta, and then you can figure out that cos theta is again going to be 1/3. But my question is, like, in this kind of very regular geometries, why would you like to go into this mechanical process? Okay, so now let's think about, this is a question for you guys. What is the acute angle between the two adjacent planes of a regular octahedron? And your options are like this. If you understood, this was a marathon video. If you understood the ideas, you can do this question in two ways, and try whichever way you like, and let me know in the comments section what is the answer to this question. There will be some, if you don't understand this video, you might be missing some other videos on this channel, which I will post a link in the description. So the related videos to this video, which will help you understand this video better. Thank you.